Welcome to the fourth lecture of this course, Nonlinear Structural Analysis, Theory and Applications. Let us recall what we did in the last lecture. In the last lecture, we have derived the element stiffness matrix in the basic or deformation coordinates, where there are no rigid body modes. And for a beam column element, which is in 2D, which is also called a frame element, the size of the stiffness matrix is 3 by 3, because there are only 3 degrees of freedom. Okay. So, from there we will start in this lecture. So, this is again to help you recall that we have the global coordinates 6 degrees of freedom, and we have the local coordinates where also we have 6 degrees of freedom, but in the basic or deformation coordinates we have 3 degrees of freedom, right. So, this is the stiffness matrix we have derived in the deformation or basic coordinates. Okay. Now, what is the objective? So, in the basic coordinates, on the left hand side I am showing you the deformations with V and the forces with S, okay, in the basic coordinate, and in the right hand side I am showing you the forces and displacements, not deformations, displacements in the local coordinates. Now, how do we relate the two? Okay. So, we would like to derive a force transformation matrix, so that we can take these forces S from the basic to the local, and I will use a notation called B sub PS. PS stands for I am going from S to P. Okay. So, the force S is transferred or mapped from the basic to the local through this transformation matrix, which is called BPS. Then I will derive the displacement transformation matrix that will transform my local displacement, local P's, this P's to the deformation at the basic or deformation coordinates through a transformation matrix AVP. So, B is my force transformation matrix, A is my displacement transformation matrix. PS stands for I am going from S to capital P, and here VP stands for I am going from P to V. Okay. Local displacements to the basic deformations. Okay. And then I want to derive the element stiffness matrix Kp in the local coordinates. Okay. So that the force displacement relationship for the local coordinate is capital P, the forces in local coordinate, is equal to K sub P, the stiffness matrix in the local coordinate, multiplied by the displacements in the local coordinate little p. Okay. So, let us look at the transformation matrices between basic and local coordinates. How do we do that? So, here I am showing this picture again, now only showing the forces. So, S1, S2, S3. Remember, this is axial force, this is a moment, this is another moment. I want to then transform them to P1, P2, P3, P4, P5 and P6. How do I do that? Through a transformation matrix. So, my P vector is a size 6 cross 1. My S vector has a size 3 cross 1. So, what is the size of this transformation matrix? It has to be 6 cross 3, and I am calling that BPS. The question is, how can we determine this BPS? Okay. So, let us say if I apply S1 is equal to 1, S2 equal to 0 and S3 is equal to 0, right. So, and let us say I am doing this matrix vector multiplication. So, if I do this multiplication first row into first column, so that gives me this entry into S1, all others are 0 because they are getting multiplied by 0 0. Then I am doing second row multiplied by this vector. So, that means I am having only this entry because the other two are getting multiplied by 0. So, if I do this, if I apply S1 is equal to 1, S2 is equal to 0 and S3 is equal to 0, then if I do this multiplication, I get the first column, right. That means, can I say if I apply S1 is equal to 0, S1 is equal to 1, S2 is equal to 0, S3 is equal to 0 and determines this P vector, then that will be the first column of my BPS matrix? Yes, that is what it is. So, apply S1 and thus S2, S3 equal to 0 and get the P. How do we determine? Using statics, that means using equilibrium. Okay. Similarly, to get the jth column, apply only Sj equal to 1, other two are 0. Okay. So, let us do that. Here I am showing I am applying what? S1 is equal to 1. So, I have got a simply supported beam subjected to axial force S1. So, I want to determine the reaction. What is the reaction here? This reaction is equal to 1, this reaction is 0, this reaction is 0, right. But this reaction what I have drawn here is equal to 1 is in the towards left, right. But my capital P1 is to the positive to the right. So, then can I say that capital P1 is equal to minus 1, capital P2 is equal to 0 because there is no vertical reaction, P3 is equal to 0, P4 is equal to 1, it is to the right. I have already applied S1, so which is equal to P4, P5 is 0, P6 is 0, as simple as that. So, that gives me the first column of the BPS matrix, minus 1 which is this one, then 0, 0, 1 which is this one, and then 0, 0, as simple as that. Similarly, if I apply S2 equal to 1, that means now I am applying a moment, right. I am applying a moment, S2 is equal to 1. How do I determine the forces? Well, using simple statics, what I will do? You are applying a moment like that. So, this will be the reaction. What is the reaction? 1 by L, and this is also 1 by L, right. Now, I have to write down the forces in the direction of P vector, right. So, what is my P1? P1 is 0, there is no axial force. Okay. What is my P2? P2 is 1 by L because this and this direction, the P2 direction are the same. So, P2 is equal to 1 by L. Okay. P3, what is this is the applied S1. So, that is 1. P4 is 0. P5, now P5 is positive upward, whereas my reaction is downward. So, therefore, P5 is equal to minus 1 by L, P6 equal to 0. So, that gives me the second column of the BPS matrix. Similarly, I apply this is equal to 1 and determine the forces and get the third column of the BPS matrix, which is very easy, just like I did previously for the S2 is equal to 1. Okay. So, now I am showing all of them together. This is applying S1, this is applying S2, this is applying S3, and this is the BPS matrix. Remember what we have done now, that if I know the forces in my deformation coordinates, I can get the forces in my local coordinates, okay, through this transformation matrix B sub P S. Okay. Now, let us talk about the displacement transformation. Okay. So, displacement transformation, we will go from the local coordinate P to the deformation coordinate V. Why it is the other way around? Because let us recall, in a finite element analysis or in a computer analysis of a structure, what we do? We first calculate the displacement at the structure level, and that is my R, right. And then what we do? We from this R we get the Q, the displacement in the global coordinates for one element, and then from this Q we get the displacement in the local coordinate little p, and from this P I need the deformation of the element. Once the deformation of the elements is known, I can do a state determination to get the force vector S, and then this S I will take and transform to capital P local forces, and this local forces I will then transform to global force vector capital Q, and then I will consider all the elements in a structure and assemble them to capital R. These are all vectors. Okay. So, therefore, for the displacement we will go from P to V, local to the deformation. How do we do that? Well, I can use the same approach, that I want to express, I want to convert this displacement, this P's to the deformation, the V's. How do I do that? Through a transformation matrix, which I am saying A V P, it is transforming P to V. Okay. Again use the same approach to determine A V P. What? I will apply P1 is equal to 1 and all other will be held in position, that means 0. So, if I do that using kinematics, I can get what are the deformation. So, those are the first column of the AVP matrix, just like I discussed in the case of BPS. Okay. So, repeat the same thing for all other columns. So, here is one for the when I am applying when I am applying P1 is equal to 1. So, this I am just showing you to recall that these are my local DOFs and these are my deformations. Okay. So, if I apply P1 is equal to 1, what are my deformations? What is V1, what is V2, what is V3? Well, there is no V2 and V3 because there is no bending, there is no rotation, right. I have just applied P1 is equal to 1. Remember, this node is not going anywhere because all other displacements, all other P's are 0. Okay. So, what is the deformation of this element? This node has gone to here, right. The element has been compressed by unity. Okay. What is the deformation V1 then? V1 is elongation positive and I have compressed it. So, what is my V1? It is minus 1. What is V2? There is no rotation, 0, V3, 0. Similarly, now if I apply P2 is equal to 1, only P2 is equal to 1, P1, P3 to P6 are all 0. That means, I have taken this node to here, right. So, this is my chord, but the element at this end is not allowed to rotate because P3 is 0. So, that means, I have to deform the element like this, so that the rotation here is 0, the rotation here is 0, right. But then what are the deformations? What is V2 and V3? Well, let us see how V2 and V3 are defined. So, this is the node. After deformation, the node has gone to this. Okay. So, if I join, this is my chord, right. So, chord to the tangent. So, this is the elastic curve. So, if you draw a tangent to the elastic curve, okay, this is the tangent, from chord to tangent is the deformation V2 at node I. Similarly, V3, this is my elastic curve and this is the tangent. So, this is V3. Okay. So, now if you come back to this figure, this is the chord and right, this is the elastic curve. Okay. So, V2 is this angle and V3 is this angle. Once you recognize this, then it is very easy. What is V2? V2 is, if this is 1, then V2 is 1 by L. What is V3? Is again 1 by L. What is V1? It is 0. Okay. Similarly, if I apply P3 is equal to 1, all other P's are 0, right. So, if I apply P3 is equal to 1, the element has to deform like that. Okay. So, P3 is equal to 1. So, if P3 is equal to 1, what is my V1? Is 0. What is my V2? So, V1 is 0. What is V2? Well, it is the same rotation, that is unity. What is V3? Is 0. Okay. Similarly, if you apply, so this row I have explained, this I have explained. Similarly, if you apply P4 is equal to 1, P5 is equal to 1 and P6 is equal to 1, you can get the remaining 3 columns of the AVP matrix. Okay. Combining everything, this is the AVP matrix, right. And what is the relation? The transformation relation, V is equal to AVP into P. Okay. Now, let us look at them together, BPS and AVP. So, this is my BPS matrix and this is my AVP matrix. What do you notice? You see that BPS and AVP are transpose of each other. So, force and displacement transformation matrices are transpose of each other. AVP is equal to BPS transpose, as simple as that. Okay. So, with that, now let us talk about how do we determine the element stiffness matrix Kp in the local coordinate. Okay. So, the force displacement relationship in the local coordinate, capital P, remember capital P are my force vector, are my vector of forces, right. Capital S is the vector of forces in the deformation coordinate and this is in the local coordinates. So, capital P is equal to BPS into S, which we just now derived. So, I can write S is equal to Kv into V, because this also we have derived. This is the force is equal to stiffness matrix into deformation. Now, V I can write the deformation in the basic coordinates is equal to AVP into P, I just now derived. So, BPS into Kv into AVP into P is what? So, on the left hand side I have force in the local coordinates and this is the displacement in the local coordinates. So, what is this quantity then? This is nothing but the stiffness matrix in the local coordinates, which we are calling K sub P. Okay. So, stiffness matrix in local coordinate is BPS into Kv into AVP and recall that this and this are transpose of each other. So, I can write this equation is equal to AVP transpose KV into AVP, as simple as that. Okay. So, if you do that, if you I have already determined what is AVP, I have already determined what is KV for a beam column or frame element in 2D. So, if you do this computation, then this is the stiffness matrix you get. It is a 6 by 6 stiffness matrix, which now look familiar to many of you, because you have done this direct stiffness method for linear system, right. This is the stiffness matrix that you would get. Okay. Now, let us go from local to global, okay, or relate, determine the transformation matrices. In the global coordinates, remember, capital Q are my forces and little q are my displacement. What is the force displacement relationship? Capital Q is equal to the global stiffness matrix times the global displacement vector. On the other hand, in the local, capital P is equal to Kp into little p. Now, we have to determine the transformation matrices, which is easy, and many of you have done this in your structural analysis class. Okay. So, these are the forces in the global, except that my notation is capital Q and little q for global and capital P and little p for the local. Okay. So, if I look at this node I, okay. So, what I want to do, I want to express this P1, the force in the local coordinate, and P2, resolve this along Q1 and Q2. So, I can write Q1 is equal to P1 cos theta. What is theta? This is the angle theta. P1 cos theta minus P2 sin theta. Similarly, Q2 is equal to P1 sin theta plus P2 cos theta. What is Q3? Is the moment, which is same as P3. So, Q3 is equal to P3. Similarly, you repeat the same thing at node J. Okay. So, now I have a relation between the capital Q's and the capital P's, which is what we are looking for. This is the relation we are looking for. Capital Q is equal to BQP into P. That means, I am taking this forces P and going to the global forces capital Q. Okay. So, writing this equation in matrix form gives me BQP, which is this cos theta minus sin theta, then all zeros, sin theta cos theta all zeros, and this is 1. Okay. So, you are quite familiar with this BQP. Okay. So, this transform the local forces to the global forces, right. Okay. Now, can we do the same thing for displacement transformation? Remember, for the displacement we will go from global to the local. Okay. So, Q to P. How do I do that? Well, displacement is also a vector. Okay. So, at node I, if I apply Q1 displacement, okay, and Q2 displacement, or one at a time, let us say, then I can always resolve it into the direction of P1 and P2. Okay. So, at node I can write P1 is equal to Q1 cos theta, this one, this direction Q1 cos theta plus Q2 sin theta, this in this direction component is Q2 sin theta. Similarly, P2 is minus Q1 sin theta plus Q2 cos theta. I am just resolving and taking components in the direction of P1 and P2. What about P3? Well, it is the same, Q3 is same as P3. Okay. So, this is what I get at node I, and at node J similarly these are the equations that I get. So, if I write them in a matrix form, then on the left hand side I have the displacement in local coordinates, on the right hand side I have the displacements in the global coordinates. I am transforming them through a matrix A, P, Q. So, remember the notation, P is on the left hand side, Q is in the right hand side, I am transforming Q to P. Okay. So, this is the transformation matrix A, P, Q, right. And observe, you have seen the B, Q, P, and now you see A, P, Q. What do you find? They are transpose of each other, and that is the property. The displacement and force transformation matrices are transpose of each other. Okay. Okay. Now, we can formulate the stiffness matrix in global coordinates, having determined the transformation matrices. So, I will start with this relation, capital Q is equal to the forces in global coordinates is equal to a transformation matrix multiplied by the forces in local coordinates. Then this forces in local coordinates I will relate it with the displacement in local coordinates. So, Kp into P, right, this remains as it is. Then I will do this P, that is the displacements in local coordinates will be related to the displacement in global coordinate through APQ into Q. The remaining two remain as they are. Okay. So, now on the left hand side I have force vector in the global coordinates capital Q and the displacement vector little q in the global coordinates. So, force and displacement, what is this quantity then? Stiffness matrix. So, this is we are calling K sub q. Okay. So, the element stiffness matrix K sub q is BQP into KP into APQ, and remember these two are transpose of each other. So, KQ I can write APQ transpose KP into APQ, right, as simple as that. Okay. Now, can I go directly from basic to global? Yes, it is possible. Instead of going from basic to local to global, I can directly jump from basic to global. It is possible. How? Let us say I can write the global stiffness matrix KQ, which we just now determined, APQ transpose KP APQ. This is what we just derived in the previous slide, right. This is what we derived in the previous slide. Now, what I am doing, so APQ transpose remain as it is. This APQ remain as it is. So, KP I am writing, if you remember a few slides back we have derived AVP transpose KV into AVP. So, this KP is the local stiffness matrix in terms of the basic stiffness matrix KV. So, AVP transpose this. Now, if I consider this two term, I can write this is AVP into APQ whole transpose into KV, and this is AVP into APQ. Okay. So, this quantity let us call it by a different name, drop the P. Why? Because local coordinate is dropped. So, I will say AVQ transpose KV into AVQ. What is BQ then? BQ is the displacement transformation matrix between global and basic degrees of freedom. How? Let us prove it. So, if we go from global to basic, then what we can write, V is equal to AVP into P. This we have already derived. V is the basic and P is the local, right. Now, this local I can write APQ into Q. Okay. So, now this two is what as per my definition AVQ. So, AVQ into Q. As you can see, right hand side I have the global displacement, left hand side I have the basic deformation. So, I can directly go from the global displacement to basic, but we have to be careful when we deal with geometric nonlinearities, that we will discuss in the later in the course. Okay. So, how do we do that? Well, I have already derived AVP and APQ, you just do multiply it, then you can directly get AVQ. So, V is AVQ into Q, if you just do the multiplication of this and this is the matrix. What is the size? It is, what is the size of AVP? This size is, this is 3 rows and 1, 2, 3, 4, 5, 6 column. Why? Because as I have shown here, Q is 6 cross 1, V is 3 cross 1. So, this must be 3 cross 6. Okay. Similarly, I can determine the force transformation matrix. Remember one more time, we calculate the displacement at the structure level, from there we choose one element, get the element and displacements in global coordinate. Then from global we can directly go to basic and determine the deformation. Once the deformations are determined, I do a state determination to get the element and forces, right. And those element and forces from the basic, I will have to take them to global. So, how do I do that? I can directly go from S to Q through this transformation matrix BQS, which is easy to show that it is equal to BQP into BPS. I have already derived BQP and BPS. If you just take the product, this is the transformation matrix you would get. And it is easy to see, going back one slide, that this and this are transpose of each other. Okay. So, BQS is AVQ transpose, as simple as that. Okay. So, let us summarize what we have done in this lecture. So, for the stiffness matrix, what we have done, we have determined the stiffness matrix in the deformation coordinates. There are no rigid body modes, we often call them basic coordinates or basic system. Then from there we have gone to local coordinates, okay, where the x axis is along the element length from starting node to the end node, y axis is perpendicular to that and the theta axis using right hand rule. Okay. So, we have gone to local coordinates, then from local to global coordinates, and then we will assemble, which we will discuss, to get the stiffness matrix at the structure level. So, in using the notation Kv to Kp using this transformation, then Kp to Kq using this equation, then Kq will be assembled to get the capital K for the entire structure. For the deformation, how do we calculate element deformation? At the structure level, we have solved for r, little r, then we extract for the element that I am studying. Let us say a structure composed of many elements. So, we take one element at a time and get the q's, the displacement in global coordinates. Okay. And then from q, I transform it to local coordinates little p. Okay, using this transformation matrix, and then from P I go to the deformation phi, and I have also discussed that I can go directly from here to here. Okay. Then for the member end forces, we calculate in the deformation coordinates, because imagine you have a nonlinear beam column element, which we will discuss in this course. Okay. Once you know the deformation, you can do the state determination and determine the member end forces for a nonlinear beam column element. So, S is known, let us say. Then how do you go to the structure level? So, S you transform to P the local using this BPS, right. Then from local to global using BQP, and then consider all the elements present in a structure, assemble them to get the R. Okay. So, this is where I will stop today and will continue in the next lecture on the direct stiffness method. Thank you so much.